All right. Welcome back. How you doing? Another week. Some more Haskell hacking. I'll be your host for tonight. I'm Agent Ultra. Pardon me. I'm just coming over a little bit of a cold, so I got my nice throat coat tea. It'll help me through the evening. Hi. So on this channel, on this stream, I basically do programming in the Haskell language mostly. And we build libraries and tools and games and fun projects just to get a handle on the language, learn new things, and just show how practical it can be. Sometimes we just mess around, find out. So anyways, for the past little while, we've been working on learning the wave function collapse algorithm. This is an algorithm for procedural generation of usually of textures, but you can generate a lot of things if you put your imagination to it. The basic idea of it is that it takes a small seed input image and can generate a larger image with like kind of similar locally similar properties. You hopefully we'll get the idea. We're on the visualizer part now at this point in time, and that involves loading a bunch of pixel data from different image formats, and well, in this case PNG, and then loading them into a texture in SDL and then rendering that texture out. I'm trying to write some code that gets that texture data out of gets the raw pixel data out of the texture, loads it into our kind of grid data structure for the algorithm to work on, and then take that output, we get an output grid back, and then put that back into a texture and render that in SDL. That's our goal. That's what we're working on. So let's get into it. I think we left ourselves with a little challenge last week. We kind of nailed down what's happening here with the visualizer. We get into the code here. Basically, we want to load the image using SDL's like image library. Normal stuff here. Oh, my cat on my keyboard. Okay. And load the image, and then our from surface function loads this into our input texture format, or a texture format, which is like poorly named, but it's basically like our little grid type of data structure that can hold like raw data of some kind. And then we want to basically render that back out. Do I have that stashed somewhere? My test was basically going to be let's see. I'll save it, sure. So the test there was going to be basically, let's load it into the texture, get it out of the texture, and then render. That's too many textures. Load it into our like input texture, back out of our input texture back into a surface, and then render that surface. That was kind of the idea, I guess. And as long as we could do that without wrecking the input image, then at least we know our like to and from functions work, right? Let's see. Debug. No, this is not the one we want to apply. Don't want any of those. Okay. I'll get rid of that. Gosh, what is going on here? Untracked file. I want to get rid of the stash. Okay, anyway. I thought I had a stash somewhere. I might have actually got rid of it. So input texture. And then we want to go back to a surface. Ah, that's what's wrong. Okay. Sometimes I use this thing called Power Toys on Windows. I don't really use this machine for much other than like coding and playing the game sometimes. Yeah, anyways, I use this Power Tools thing, and sometimes it messes up the keyboard state. There we go. Hopefully that, so much better. Okay. So right, we're gonna go back to an image. We're gonna go to surface from our input texture. Perfect. I think this include, yeah, the updates we did last week. Get pixel up to surface. That should be all good. So go from surface to surface, and then we're not going to print that out, but we're just going to render it on the screen. Oh, okay. Actually, we're already doing that. Perfect. Input texture. Okay, yeah. So we load it. We get the input texture. Okay, we do some stuff with it, and then. Oh, this is the output stuff after running the algorithm. Instead, comment that out. Make image prime. To surface. Input texture. Okay, and then we should render that. Input texture. Yeah, and run that. Okay. So the goal of this is just to see that we can load the input image, and we can render it back after converting it to and from our data structure here. And if we can get that going, then we're gold. Because I'm pretty sure, fairly certain, the algorithm itself internally doesn't actually manipulate any of the data inside the texture other than like grabbing values and moving them around kind of thing. It's the values themselves that we're having a bit of struggle with here. So let's get our builder going. Yeah, there's our test image. And then hopefully, this probably won't work. It'll probably render the garbage we've been seeing. Some kind of dark blue color of some kind. Come on. Still a bit slow because we're running the algorithm. Maybe we could turn that off. So we can iterate a little faster on this. But yeah, this is the junk we're getting right now. Junk data. And that's because we're doing some pretty low-level stuff with the textures here and like the pixel data. We're reaching into raw C arrays and pulling out data from somewhere in memory in Haskell. So, and then putting into a data structure, manipulating it, and all that stuff. So that's what we need to fix. So close that up. We'll get back to main. We'll just... Let's get rid of... Copy this up here. Put it here. App loop. Copy that there. And You know what? Actually, I'm gonna undo that. I'm just gonna call app loop here with our image texture and the renderer. And we can just comment all of this out. There. Now it should be a little bit faster. There we go. Okay. Cool. So we're just going to be focusing on toSurface and FromSurface. FromSurface and toSurface. I think we did quite a bit of work on FromSurface last week. Let's just review quickly. All right. When we call FromSurface, we get the with_surface function here on image to get the image surface. That's the raw... no, it's just a surface. Type surface. Okay. We got the surface dimensions of it. And I think with_surface locks it, yeah. So we get the surface dimensions. We print that there. And unless it's a square, we error. Oh, input image needs to be a square. And then we get this pixel pointer. This pointer is the pointer to the raw pixel data that comes with the surface through the C struct on the C side of things in SDL. So we get the surface pixels from that, the pointer to it at least. And then this collection of pixels that we're calling them. We call this get pixel function on the image surface with the pixel pointer with this x and y values. These x and y values are coming from like our kind of pixel coordinates into the surface, I guess, from 0 to image width -1 and 0 to image height -1. And then we call this WC texture from list. So this texture from list function is like the library's internal thing. It just wraps it up in our aptly named texture data structure. All right, that just looks like this. Let's just bring it up quickly. Source, algorithm, main function collapse. All right, texture, pop, pop. All right, it's just an array, two-dimensional array of words. All right, so I did a little look because yeah, it's okay. I think this might be putting into a two-dimensional array. Hopefully it's the right order of things. I guess we're gonna find out. That could be one area of things. So depending on how that pixel data is packed into the C side of things, right? In STL's kind of internal format for things. Hopefully we're on the same page here with like how the pixels are laid out in the XY pattern, you know. So texture from list anyway. That's the main one. Construct one of those. Because it's square, it only has to take the size, one size. And then the list of A's. Let me give a texture of A. And so the reason why this is like A is like a polymorphic type variable. We don't know what type it's going to be. We didn't want to like decide what the pixel format is or anything like that here and name it. So we just abstract say it's an A. I don't really know. If we don't say anything about what type this A is or what constraints there are on that A, then we don't know. We can't do anything with it anyway inside this function. Like, there's no function in Haskell that would accept just an A and be like, okay, yeah, cool. If it tries to like do anything with it by like applying a function to it or something. So we can only just pass them around. Can't do anything with them. We can't call things on them or change the data or map them or anything. So we get this array.array from 0, 0 to size 1 minus size 1, size minus 1. We take the rows of size. So I think rows cuts down that flat list into chunks of rows. Coordinates. X, Y, X, Y. Texture from list, that's what it does. makes a list of lists from the input list, calls array.array on it to construct the array, and then plops that in the texture constructor. Pretty simple, hopefully. Now to surface. Alright, let's move on. To surface here. Okay. So we get that texture type I just showed you. And we're calling it CUInt, but we're allowed. We're the caller. So we're telling when we say it's a CUInt inside this texture, then it's a CUInt as far as Haskell's concerned. And that's okay. All right. So array.bounds of our array gets the size of the array, the width and the height. Here, I think this first element is the array itself. Or maybe the number of elements, but width and height there. And then from integral here, TWI, texture width -1, index maybe. Poor naming. Might need to rewrite this. Anyways, so we get some intermediate variables here, basically like the size of our input texture and maybe an index. Our output is we're going to create an RGB surface. That's from SDL. Creating a surface object. From integral, so we give it the size of the surface. Should be the texture width and texture height of the array bounds on the texture here. And this pixel format, RGBA8888. That could be a potential source of our problems here. When we're loading the texture, we're not really saying so much what this format is. I think we're implying that's, maybe we should write this down. It's like a 32-bit. I'm assuming they're a 32-bit packed format. Right. We have RG, B, and A, each being a byte each, giving us 32 bits. I think that's what that actually means, RGBA 88888. So we create an output surface in that pixel format. Then we lock the surface again. Yeah. Using the bracket pattern. Lock surface, unlock surface. And we get a void pointer. We cast it to our pixel pointer. And then we sequence this set pixel function. And we take the array the association list of the array. So that's each index and its corresponding value together in a list. Tuples. That's what we get here. X, Y, and then the value V. From that array. And then we're going to call setPixel in each of those X, Y, and V values. So setPixel takes the pixel pointer, calculates, it looks like some value, some offset here. From integral Y times CWI plus 1 X. It sets the V. And what does setPixel do? I'm guessing just pokes byte offset. Just poke byte offset. So just pokes at that pointer array. Some offset of bytes from that base pointer. And then a value. And just puts it there. Okay, so this offset could be wrong, calculated wrong. And that might be the source of our issue here. Because if we go on the other side from surface, Right, we had to calculate the, when we go to get pixel, we had to get the bytes per pixel there. We had to get the pixel pointer and our pitch. We had to consider the pitch based on the surface width of the raw surface from it equal the bytes per pixel. And this formula here is what calculates our byte offset. We're doing peak byte offset here. And so I assume on the mirror side of things, we should have like a similar formula, excuse me, for set pixel. Try not to do that too much on stream. Sorry, Chad. So there you go. Let's work on that. Hmm. One thing I'm noticing right now is that on getPixel we're calculating, we're peaking all of this stuff. It's not that bad chasing those pointers, but we probably just need to peak them once. You know what I'm saying? Anyway, we'll fix that up later. Yeah. So let's make set pixel look kind of like get pixel. We'll pass in the surface output in. Okay, and then we're gonna get the raw surface. In fact, we're gonna do, I think we can get all of these. Actually, we need a pixel pointer too, and well, that's already calculating the offset, but we're going to actually get rid of that. So we'll just do the value of the pixel data. I'll just name it pixel data. So if we get that in there, we don't have to cast anything there. Right, so the surface pointer we have to pull in here. Like that. And that's the problem there. Oh, an argument issue? Yeah. Okay, and then we need a poke byte offset here. We give it the pixel pointer. We give it the offset. Take that, and the data that we want to put there. Okay, and then we're going to have another issue up here we call set pointer. Our set pixel. Just had to get rid of the offset calculation here. And then I think we'll be good. Not quite, but almost. Where is it? Ah, X and Y are not in scope. So let's pass those in instead, just like we do with get. cint, cint, uint, x, y, pixel date. Oh, okay. Yeah, that's just a simple little type conversion error. So our text is getting a word here. Word. I wonder if that'll fix it. Just more from integrals. Awesome, defined but not used. 98. Let's get rid of it then if it's not used. Okay, cool. Slightly different data. Okay. Prague, maybe? Let's see. Well, we're getting slightly different data. Still not the one we want, though. We want the input image. Does it look kind of like the input image? Maybe. That's what it looks like. Data. Right. Oh, if I can open it just fine here. I think it, no, it's going to be small and Emacs can't be sized. Oh, but it does. Okay, that's our image. Our image data. And that's the texture we get. So something I'm noticing here. They kind of got the same shape in some ways. Just rotated. So that could be the rows thing, the way that the pixels are actually being packed. It's getting stretched a little bit, so... yeah. I got the same kind of shape in these places. But the colors are all completely borked. Okay. So it could be our workaround to try and get the pitch. It's a bit of a hack, the code we have there. It might be wrong. It might just be that we have no way of, you know, like our hack just isn't, this hack isn't going to work. That's one possibility. But let's. So the rotation issue though would be something we could fix. Okay. when we get our data out of the surface and we put it in our texture from list. Texture from list is treating this as one giant continuous list of pixels, and assuming that it's in row major order. So it's assuming that like each row is kind of packed in one after the other into the array. Oh no, not epic. Epic pen. Go away. Right, and so when it's turned 90 degrees, rotated. Oh, it looks like it's almost rotated 90 degrees, but I think that it's not like doing everything. I think we're just selecting the data out differently than we think, and we're not packing into this list in the order that from texture from list is like chunking it. Right. Let's see if we can make it a little bit more visible. All right, so we have this like contiguous array of memory, and like the pointer is like the base address of it. Right, and we're kind of assuming that like we have one row, two rows, three rows, so on, right? If it was like a 9 by 9 square, and it'd be like 3 elements each. And that's where texture from list is assuming that like these are all packed together in that order, because it's going to chunk them into 3 by 3s if we pass in the image width as 3. This expression here, though, pixels, right? The order that getPixel is being called in, right, for each x and y, what's that going to be? Right, think about it. Well, the first iteration, that's going to be 0, 0. Right. So that would be, in this packing here, that would be this pixel here. 0, 0. But what's the next one? I think it's going to be 0, 1. Which is going to be this pixel over here. All right. And then 0, 2. All right. So when the texture from list function gets all of this data lined up this way and like does the chunk 3 by 3, but these pixels are packed in this way, it's going to look rotated. Right? Hopefully that's right. You're going to yell at me, chat, if I'm about to like walk into a wall and hit my nose on a pole or something. But I think that's how it's going to go. So what we need to do is make sure that this list is in the order we expect it in, or change texture from list a little bit there. All right. Let me just test this through quickly in the REPL. So we go x, y, right, x, 0 to 3 minus 1 would be 2, and y from 0, 2, 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, 0, 2, 1, 2, 2. What we want is 0, 0, 1, 0, 2, 0. Yeah, 0, 1, 1, 1, 2, 1, 0, 2, 1, 2, 2, 2. That's how we actually want them. I want the columns increasing and then the rows increasing. So they're in row order. So let's see if that works. Let's reverse the arguments. And if that works, that's just going to flip that that poorly colored image. It's not going to fix the pixel coloring. But it should flip it around. Okay. It did, but not in the direction I was thinking. My XY. Maybe it's because I did it the wrong way. That's the wrong function. Oh, we might I messed up something there. Yeah, it's seg fault. Probably because we access something out of bounds of the array. XY, the association lists of the indices from our array from the texture. Those should all be in bounds. Interesting. Looks right there. Bank formula. Okay. Going from surface. Get the pixel at XY. If we flip these ones around, we load the texture. What do we get? Default. Looks like we started it before it finished building. There we go. Okay. Let's rotate it around the right way. Now, what the hell's up with the values? That's the only other thing now we need to understand here. What is going on with the data when we set it back into the surface texture? We pull it into Haskell. And we put it back. That's all we're trying to do, is we're trying to pull it into a Haskell data structure out of this C array, put it back into a C array. It looks like we've got the right structure, but the values are not right. What could that be? Hey, Garoptical, how's it going? Nice to see you. Thanks for popping by on the stream here. If you're just catching up, We wrote a little wave function collapse algorithm. We're trying to write a visualizer for it. But we're running into some fun low-level stuff with SDL and the Haskell bindings, loading image data and stuff like that. Awesome. Well, lurk away, friend. Interact when you can. Are you streaming again? I hope you are, or that you will be soon. If you feel up to it. Awesome. I'll catch some of yours too. Okay. In the morning. All right, all right, all right. Interesting times. I'll check your schedule out. Hopefully the link above my head is still correct. Power Optical is one of the folks that runs that website. Okay, so what else could be going on here? It could be that, like, maybe our offset from the base pointer is wrong. You know what, Optical, you do it when you can, right? And you fit in the time when you can. I know what it's like. I've been there, my man. Been there. Done that. I got new things now. Now my kids are much bigger and older, and they're starting to become teenagers. That's a whole other world. A fun one, though. My eldest, we got her her first PC for Christmas this year. Or last year, I guess. And, I mean, we got it because she wanted to, like, she's been pulling my leg to, like, help her set up her own website so she can, like, publish her comics and stuff with her, so she can show her friends. And I was like, okay, yeah, well, obviously gotta get you a computer to set that up and do it, because you're not gonna use mine. So, yeah, I got her set up with that little Wacom tablet, and she also wants to do animations. She's been doing animation and stuff, and just blowing my mind with how fast she's been able to pick it all up. Super fun. Yeah, that's teenager level stuff. But yeah, soon she'll be hacking the HTMLs and making a website, and all that stuff. Meanwhile, I am digging into hacking things. So, the annoying thing with this wrapper that we discovered is this issue with the SDL2 wrappers, where it doesn't give you access to the pitch of the surface. So, like, in most image formats, like, the pitch is like when you pack the different color values into a single value, and you want to know, like, how to calculate the offset to a given pixel from a base pointer, right? You need to know how many bytes to skip. That's called the pitch per pixel. So we've had to, like, kind of sort of calculate it. What I'm thinking maybe is that our calculation maybe is a little bit wrong, which is why we're getting some of the data, kind of, but it's the wrong color. Right? It's the right shape-ish. Right, except for this column here on the far left. I think those are wrong. These all here, like, seem to have a similar shape to our input image. So this could be just, like, random junk data somewhere in my memory, and this could be all good stuff. And if we're just a little off, fix the offset, maybe that'll fix it. So it could be the pitch that we're getting wrong, or it could be that our base... What is it? No, our base offset is just coming from the raw pointer. We're not starting off anywhere wrong, right? I'm gonna go from surface. Alright, we get the surface dimensions for the image surface here. Check that it's a square, and this pixel pointer is passed straight through to get pixels, so yeah, we're not doing any offsets from there. X and Y here. Really, I should just put these around Y and X. Then we can actually put these in X and Y here. Run it. Do the same stuff. No, maybe not. No. Fragmentation fault. No. Why? Oh, maybe I started it fast. I don't know. Or finished building. Oh, I messed it up. There we go. Yeah. Okay, maybe not that. So, let's see. Gotta be in here, I guess. So I think CUint is the right type to cast there. I think we verified that last time. It's a unsigned 32-bit integer format. So it could be that our pitch calculation is just like crap. Let's see if I can offset it a little bit. Maybe it's the width. Maybe it needs to be 0 indexed. Oh, that's terrible. Agent Ultra. Showing off textures generated from data somewhere in his RAM. Somewhere close, though. Somewhere close in the RAM. We're almost there. Okay. So the byte offset here, let's just like... we kind of like copied it from the issues here, but let's just try and think about it a little bit here, what it means. So this Y passed in up here is the row that we want to get. We multiply that by the pitch, looks like, so row by the pitch. So if we want to get into the second row, 3. So the pitch is like, that's going to be in bytes, I think. Bytes per pixel, yeah. So raw surface width times bytes per pixel. Actually, no, it's gonna be how wide it is, right? So the row times that pitch is going to give us like an index into, if it's row ordered, I think it's starting to look a little bit like it might be, maybe. Draw it out when in doubt. All right. Normally I would... Yeah, so pitch is going to be the row width, I'd imagine. All right, the width of the surface times the number of bytes in that row. And so my width is 5 pixels. Then I need the number of bytes, so I'm going to multiply that by the bytes per pixel. And it's 32. It's going to be like 5 times 32. All right, that's going to be the size of a row of pixels. All right, so y times that is going to give me which of these yellow blocks in this array, right, of pixels, so on and so forth. And then we add into that number x, so that's the column, times the bytes per pixel. Remember, bytes offset. And so if we want this little pixel in here, all right, we're going to add a number of bytes from our offset, our y offset, to get our x based on the bytes. So if this is going to skip 32, 32, 32, 32. So we want the fourth one, 1, 2, 3, 4, skipping 32 bytes each so that we get the right bytes there. So I think that's right. I think so. That sound crazy to you, Car Optical? I don't know. I think that's right. Okay. I'm just going to take a quick peeky at that issue again. Let's make sure, double check that we've got that. What they had as well. Yeah, pixel format, bytes per pixel for the pixel format. And surface width for the surface times format bytes per pixel. That gives the pitch. Oh, GitHub picked up the fact that I mentioned it. Oops. This is the struct, so this is the value here that we're trying to compute and work around. Not being able to get. Yeah. All right, so what else is there? Well, we go to setPixel. We get the array association list. I think. I don't know if the order of this one matters so much, just as long as we get all of the values and set all of them. Although, no. I mean, if you think about it, right? Kind of paint. In some order, you're setting each pixel, and each of these should be discrete values, but not over. I think it doesn't really matter how many. Well, it wouldn't. It might matter to. Well, I don't know. I was thinking it might matter to the SDL surface, but if it did, I think we would be seeing wildly different results if, like, I wasn't right about the way it's packing the bytes into the surface format for the pixels, you know? Right. we're getting the kind of shape of our input image, but yeah, it's just off a little bit somehow. So it could be that we're maybe setting it. I mean, we're using the exact same code. Well, okay. We're not using the exact same code. We're just this is just the code to get the pitch that we were getting. Pixel. Okay. Yeah. So what this is saying here, if I understand it, is that for us at least, when we go to create the output surface that we're gonna render to, up here. Oh no, way back here. Yeah. Yeah, we're doing it to surface. Sorry, not that far back. No, we do tell it the format RGB A8888. Okay. I'm just gonna mess around with that value and see what other ones we get. So maybe the getter function is like loading the pixel data in just fine. Everything's loading the pixel data just fine. We're just not using the right palette, essentially. It's possible. So SDL bindings for Haskell. It goes into raw video. Palettes. Yeah. I think that's what PNG would be, yeah. But maybe we're wrong about the input image format. I wonder if there's a way in Krita for me to tell that. Yeah. The other thing we could do is like forget PNG. Let's just go with like an indexed bitmap. All right, that's our input image. File view image properties 1212. So RGBA alpha, 8-bit integer channel. Yeah. That's got to be, yeah, 8-bit integer channel at 34. Well, unless I don't have alpha on, maybe? 1212. RGB slash alpha. Yeah, so I think that means that that'd be 4 channels. That'd be 8 bits each, 1 byte each. Maybe 32 bits. Uh, 12 by 12. 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 11. Not that. Yeah, I can't, like, it does, I don't think I need that, just makes sense. But I think that is RGB alpha. 8888888. I run out of tea. Oh man. Okay. Let's just mess around with them, some of these though, just for fun. ABGR8888. And I think we'll probably see some different colors in there rendered. Yeah. Pretty wild, right? Okay, why don't we try BGRA? Right, slightly different. Interesting that the colors are like slightly off, like different, even though on like some of these adjacent pixels they should be the same. What's up, Squeaky Sovereignty? You just got banned. And reported. Actually, interesting. I wonder if the set function offset is just a little something we got to do slightly differently there. If we try something with fewer than 4, RGB 888. A little closer. But notice this black line on the left here. Seems like we just gotta over a little bit. Now, I'm not sure how that would go if that's like from this list that we're generating, or it's in the pitch and offset. Get more like lower level down here. That's not going to be good if X is 0, probably, though. It's, well, now we got a pixel in that left column, at least. Hey, what's up, Chandu16? How's it going? Welcome to the stream. Okay, looks like we're... Maybe that X offset is. The offsets are wrong. What we're building, we're visualizing, is something called... well, there's this algorithm called wave function collapse. It's called a procedural generation algorithm, so... The idea is it works from this small input image, and then it can generate much larger images based off of that input image. And so in the larger image, you'll find a lot of local similarities, like similar patterns in small areas of the input image. And it'll look kind of like all interesting and weird. And people use them for generating textures, for generating levels in games and things like that. You could... With a little creative imagination, you could generate all kinds of things. Right now, we're just working on the visualizer for the algorithm, the front end of it, using SDL. And just struggling a little bit with the input image formats and stuff. And trying to get them loaded into our algorithm and back out again. While maintaining the pixel data. Access to the raw pixel data. So graphics programming is save from LLM Gen code taking over stupid dev jobs. I don't know about that. Who knows? Maybe we're not safe. Maybe we are. Yeah. Personally, I don't think we have anything to worry about from LLMs. I don't think we're going to be replacing our jobs anytime soon. I think what we do have to worry about are capitalists who own the companies and the money that provide our jobs kicking us out, essentially. It's the capitalists that will do it, not the LLMs. The LLMs have no... They're just algorithms. They don't do things like that. People do things like that. You know what I mean? Right? Like if I could hire a bunch of programmers, right, and get like 80% of like their productivity out of them, and then I start using LLMs, and then I get a little bit more out of them than I normally would have, a little more output for their 80% effort. Right? It's pretty good. It's a pretty good deal. If we could make the LLMs take over more of their job, then I could hire a few of them and maintain the same level of output, you know? And that would be a good strategy for me as a capitalist because I make my profits off of the labor of others, right? And so if I could pay them less or pay fewer of them and still get the same output, then I make more money. Yeah, well, there's that. So hopefully. In the meantime, I think I don't know, I'm a little mildly concerned. Maybe they'll sort it out, but I am mildly concerned that like a lot of the training that all the energy that goes into training the current gen models is huge. Right? They've been building new gas powered plants to power these data centers or back up these data centers. Because the energy demands are quite high. Okay. New gas power plants, like new methane. They're not even natural gas, they're methane, right? It's methane. Not natural gas is such a dumb word. It's methane, which is a really bad GHG. Really bad. Worse than carbon. Shorter half-life, but it retains so much more heat. Right? And that stuff leaks like a sieve throughout the entire system. So that the fact that we're putting more of these power plants online just to power AI is like, I don't know. I don't know what we're thinking. Hopefully they'll get more efficient and all that stuff over time, and everyone's like, of course they will. But, yeah, I don't know. If we don't burn the planet first, maybe the open source ones will be good and take over as the good tools. Yeah, gotta make the money back, that's for sure, right? And what better way than to be the person selling shovels to the gold rush. Right, and a lot of the people that are funding this stuff are monopolists. Let's face it. They don't like competition. And pixel formats, yeah. Not a huge fan of this. I'm kind of like at the point now where we've been working on this part of the visualizer enough that I'm like, I want something easier. This was not supposed to be the most intense part of the project. Yeah. That's the thing. I don't think the code necessarily is valuable. I think the thinking is valuable. And, excuse me, cat. Just go over there. And the value we bring as programmers is more like the theory building that we do, as Peter Nauer would say. But yeah, writing code is fun, for sure. But the value, the value that you get from it is like, it's an artifact of the theory building, like the idea of how you model the world, how you represent it in the structure of your program, and how like the system that you're kind of building for the real world, for the people involved, and for the machines that are operating. It's a very, very complex kind of thing. It takes a lot of context and intuition. Right, and code is just the artifact of that, the output of that, which is totally fun. But, so even if it's not valuable, I'm sure humans will still do it just because it's fun. Just like I still repair old tape machines and game consoles from the early 80s. And program on this stream because it's just fun. So I'm not terribly worried about LLMs. They could be pretty cool, maybe, if they fix the technology and make it better. if we fix the social issues around them. As I was mentioning, the capitalists will take your job, not the LLMs. Okay, so I think this x minus 1 term here in this expression and the resulting image that we get is kind of showing my theory that maybe it's the pitch offset issue with our indices that's causing the problems, perhaps. I'm going to see if I can switch this back to RGBA with another 8-bit channel. And if we get our original colors now, that would be super cool. Rats, we do not. What to do, what to do, what to do, what is happening? So if it's not getting the right pixels out of the array, or if they're not the right color that we're expecting, are we not, but we're getting the right kind of like, we're getting pixels in the right place, they're just not the right values. That makes sense. Also, maybe this isn't much of an issue, but it's only rendering a part of this, looks like. We're not getting the bottom row there, but it might be, the bottom row might be in there, just might be getting stretched off screen a bit here. Or it might not be getting it at all, actually. That's a possibility too. But like, it's got 1, 2, these 3 pixels kind of look like those ones, but even between these 3 values, if you, I don't know if you can see it on the stream, but like this one here is just slightly off color from the 2 preceding it, whereas it should be the exact same. Right. So we're getting data from like the right place, or like, sort of. But we're getting like not the right values, you know? Like these should all be same. We're missing a row of pixels here, I think. Actually, no, that's fine. We're not missing a row of pixels there, but yeah. That's fine. Even these pixels here, they should all be the same value, but you can see they're slightly different. So this might mean that we're setting... Maybe we're getting junk... We're reading junk data in. But we're setting it in the right place. I wonder if that could be the issue. Maybe we should look up some documentation on SDL surface pixel format. Surface. Pixel array. From left to right, top to bottom. Yeah, okay. So the pixels are arranged in memory in rows, with the top row first. Each row occupies an amount of memory given by the pitch, sometimes known as the road stride. Within each row, pixels are arranged from left to right until the width is reached. Each pixel occupies a number of bits appropriate to its format, with most formats representing each pixel as one or more whole bytes. In some indexed formats, instead of multiple pixels, in some indexed formats, instead, multiple pixels are packed into each byte. Okay, so I think what this is saying then is that we could have RGBA 8888, so 8 bits for each value, but those 8 bits could be packed into 1 byte. We could have 4 bytes. We'd have a 32 byte value, or 32 bytes of data, with just those 4 channels in it. And a byte order given by the format. After encoding all pixels, any remaining bytes to reach the pitch are used as padding to reach a desired alignment and have undefined contents. Okay. That makes sense. So when a surface holds YUV format data, the planes are assumed to be contiguous without padding between them. For example, a 32 by 32 surface in NV12 format with a pitch of 32 would consist of 32 by 32 bytes of Y plane, followed by 32 by 16 bytes of UV plane. Okay. So, our RGB PNG format. What could be happening here? Like, it looks like we're getting, at least maybe because of stretching, but we're only like seeing this area here. It's like the bottom 2 rows are getting cut off a bit. Maybe just the bottom row. Anyway, so it could be that within this 1 pixel, we have 4 bytes, and just the first 8 bits of each byte is the color channel. I think that's what that's saying. If we want to get a CU in, that's an unsigned 32-bit integer value out. So we go to peek at this from this byte offset. We're calculating the offset into that row. All right, using the row width plus the x into it. Now this x minus 1 here that I added is actually revealing that extra column there. So it might mean that... I'm not sure what that means actually. Because if the x was 0, and presumably we start from 0, at least on get here. That would be -1. That would be an issue if we were starting from 1, but I don't think we are. So that's kind of... If I remove this, then we get that black column on the left side. What else could that mean? We multiply that by the bits per bytes per pixel. Which, in this case, might actually just be 1. Okay, blank column again. I'm going to try something funky here. Remove the bytes per pixel from X. Yeah, no. That was a bad idea. Maybe we don't have to do that. Definitely have to do that. Went out of bounds there. Segmentation faults. So that's fine. I'm good. Print the image dimensions 12, 12. It's 12 by 12, so that's quite right. Now, if we try to take the raw surface width of one, that shouldn't cause a crash. It might just cause we don't get enough of the right data. Oh, we do get a core down. If we get a core down. I was expecting that would be fine. I was just thinking, like, if the surface width here, the raw surface level is 12, then width of our row should, well, should still be 12 bytes. Excellent. So yeah, forget that. So. I was thinking maybe it might be off by one thing there. Clearly I was wrong. Su int. So when we do the peak and the poke, the peak byte offset, right, the type of this function, if I can bring up my REPL here, foreign. storable. Comes with the storable class. And this is the type class that lets you look into structures that you get from, say, a foreign process or foreign data. All right, so we get a pointer, and the idea is you give it some offset int in bytes, and then from that base address, it'll offset from that address so many bytes, and then read the data there. So the IOA is what's going to return the storable A. And so we say CUINT here, that means it's going to return from that. What I imagine is doing is that from that base offset, from that base pointer, calculate the offset, and then read out a unsigned 32-bit integer for us. Haskell Cat is back. Want to be on camera? Haskell Cat. She doesn't like that. So that's what I imagine it's doing. Right, and then we're storing that 32-bit integer in our data structure. Not doing anything else to it. The actual value itself. Other than writing it back into a surface eventually. CU and RGB A. Cosmos foreign.c.types. Okay. This could also, well, now, constructor says it's CU into word 32. So this is what I've been basing my logic off of, that we're getting word 32 in, out, CU into word 32. And a word 32 comes from data.word. It is a 32-bit unsigned integer. Now this documentation here says Haskell type represents the C unsigned int type, which the concrete types of them are platform specific. So normally when I'm writing C code, I wouldn't use just plain int. It's going to be platform dependent what size that is. And that's no bueno. That's why they have the integers, standard integer model, whatever. From the standard library that gives you sized integer types. I think I'm only bringing this up because maybe we're not actually reading 32 bytes of data. An unsigned 32-bit integer value. Maybe. Let's look at the storable implementation for that. Oh no. It's using macros. Like it. I can't click on that. Okay, so I don't know how it's doing it here. Where do I find that out? Ah, brutal. So the link to the source doesn't actually show you the source. So presumably, though, it is going to return a 32-bit integer. But that's the only thing I'm thinking here is that, like, gotta be the values. We have to have the indexes at least somewhat right. Like, what else could we cast this to? We do C-ints all the way through. I think it's supposed to be unsigned, but maybe it's not. I don't know. C-ints. C-ints in there, and then we gotta change view surface here. And the pixel pointer types. To surface, C-int. And from surface, C-int. C-int. There. I think we compile again, yeah. Doesn't change anything. I'm wondering the other. So when we create the texture for the output, we create that up here, to surface. Create an RGB surface with this pixel format. Okay. Maybe it's a pixel format misalignment. That's gotta be it. That's the only thing I can think of. Is that maybe this RGBA format here is doing maybe it's doing the 8 bits with the in the byte padding. You know? This value that we're pulling out when we create this WFC texture is presumably some kind of 32-bit value. Now we went from unsigned to signed. It hasn't really made a huge difference. Any difference, maybe? In the values we're getting out. We're not trying to pull out each R, G, and B component element and A component element out of each of these channels. We're just trying to get the whole blob of pixel data in 132 byte value. And maybe what we get from the pixel format we get from the input surface isn't matching the pixel format we're trying to create on the output surface. And so when we put data into that array and say, hey, render this, it goes, yep, and then indexes into the wrong things to get the wrong colors. When I changed it to RGB 888, for example, slightly different colors. All close-ish. What we want? Not quite. It's index 8, or I don't even know what all these constructors are, to be honest. Nothing. I'm hoping we're on the 32-bit RGBA, but maybe not. Well, if we just throw a little debugging in here, and let's take a peek at the size of our BPP and stuff. Import qualified debug.trace debug. Sure, got you, chat. Vengeance ECNS. It's going down. Welcome to stream. Or is it Vengeance CNS? Vengeance CNS. Stop. Okay. So debugging. Raw format. Throw a little debug.trace there. We'll just show the BPP first. Bytes per pixel in this format. Let's set it back to our RGBA. 8888. And that should be 8. I think. 3 bytes per pixel. Interesting. Let's do it here. That pixel, BPP, go BPP. Like that. At 4, yeah, that's better. That's interesting. Our get pixel BPP is 3, but our set pixel BPP is 4, so that could explain some things. Yeah. That would explain some things. They should be the same. If there are only 3 bytes per pixel. Oh, wait. 3 bytes per pixel. That's, Single pixel consists of a tuple between 1 and 4 numbers. Referred to as channels, and every number in the image is encoded with an identical format. The formats encode each number as an unsigned integer value using a fixed number of bits. Referred to in the PJ section as the bit depth. Notice that this is not the same as the color depth, in which is commonly used for total number of bits in each pixel on each channel. The bit depths are summarized in the table along with the total number of bits used for each pixel. I don't think we're getting all that deep into the animation stuff. You know, we're just trying to work with a very simple image format here, but I think I chose the wrong one for simplicity. Yeah. Okay, well, I'm learning quite a bit here about low-level formats and manipulating foreign data with Haskell. That's good. And it looks like we made a little bit of progress, but I have to call it up tonight because it's getting late and my voice is running out. I've got band practice later this week, so I gotta try and recover. Yeah, all right. I'm gonna push up what we have at least, and see if we can't, you know, maybe we should try a different image format, maybe one a little more simple. But thanks for coming out. Checking out my stream and hanging out. It's been a slice. Hope you like what you saw. If you did, you should totally give us a follow. And let me know that you like the stream. That's how I know. And of course, if you're watching in a different time zone, you're watching my VODs, I back them up on YouTube. Thanks again for watching. Like and subscribe, leave a comment, all that good stuff. Not really trying to get found out by the algorithm, but you know, the more people who know about it, the better. It's good. You know, organically, let's grow. And yeah, so the links to all my stuff, of course, is on the Metaverses. You can find them on my Mastodon profile on the types.pl server, or on my website at agentultra.com. You can find everything there, including my YouTube channel, Twitch, stream, all that stuff. GitHub and everything else where this code lives. Let's just finish up removing any traces of debugging. Okay, we're good. Good, okay. This is what we got done tonight. Okay. Let's stage that. Modify app/main. Update set pixel and get pixel offsets. Push. Okay, so all the code you've seen here tonight is up on GitHub, like I was saying. I'm Agent Ultra there as well. And this is wave function collapse. Let's paste that in the chat for you. Ow. There you go. So if you want to start, follow along, whatever, it's all good. The code's free to use. And that's it. So I usually do these streams, if you're just tuning in for the first time, on Tuesday evenings about 10 after 8 in the Eastern time zone. So you can write that down or follow along, subscribe, and set up your notifications, and you'll get notified when I go online. Occasionally I do stream off my schedule just for funsies or whatever. So that's how you get notified about those. And what else? Check out the link above my head. It's declarative.tv. The wonderful Chiroptical runs the site. It's got a link to a Discord server where we have a channel for this stream. So you can chat about your projects there if you didn't get a chance to join us live. I hang out there all the time, along with a lot of other cool people doing streaming and talking about other functional programming languages and declarative programming languages and such. So do check that out as well. And yeah, may all your monads be free and your types always check, and we'll hopefully see you next week. Take care out there and happy hacking.